My dad studied math physics as an undergrad in France in the 80s, so he told me a lot about physics when I was a kid. My parents in general bought me a lot of science books, so I think I was always interested in mostly physics. And then when I got to university, I realized that to learn the real physics, you'd need to learn math first, and I think that's how I got really into it. I remember my dad showed me, they used to have slide rules to allow you to do computations, so he had his from his days as a student, and so I played with that a lot when I was a kid. And he also had a formula book with a lot of formulas and logarithm tables and things like this. So I remember staring at those for a long time when I was a kid and being fascinated and hoping to understand the formulas one day. It's surprising to me how different mathematicians are from one another. During my mathematical journey, I encountered so many different working styles and personalities. It's really a reflection of the world. My PhD advisor told me to work on 3 problems at the same time. One which was very ambitious, one which I knew how to solve, and one which was in the middle. So when I get stuck, I can work on something else. He also told me not to be afraid of getting stuck. That means you're working on things that are at your level, I think. When I'm stuck, I try to do some computations usually. Go for a walk and let my subconscious work on it, I think. I'm going to tell you a cool way of remembering an identity in trigonometry. So trigonometry is concerned with relations between side lengths of right triangles. And so to remind you, trigonometry, if you have a right triangle with an angle theta, the cosine and the sine are the side lengths of this triangle here. The identity I want to talk about is what happens to these side lengths if you double this angle here. And it turns out, you might remember this from trigonometry, if you look at the cosine of twice the angle, it ends up being related to the cosine of this triangle by the following formula, or the side lengths of this triangle, cosine squared plus sine squared theta. Now, I'm going to tell you a way, if you don't remember this identity, of deriving it whenever you'd like, using the imaginary number I, which has the property that when you square it, you get -1. Using this number, mathematicians found the following identity, which relates the exponential and the sides of this triangle. The formula reads e to the I theta is equal to cosine of theta plus I times sine of theta. You might have seen the most beautiful equation in math, and it's a special case of this formula where you take theta to be pi. Because we know that sine of pi is 0 and cosine of pi is -1. Now we'll show you how to derive this equation from just this equation. The way you do it is you square both sides of this beautiful equation. If you square both sides, you'll find e to the I times 2 theta is equal to cosine squared of theta plus 2I sine theta cos theta plus I sine theta squared. By the formula, this gives us cosine of 2 theta plus I sine of 2 theta. And by grouping the real terms and the imaginary terms together, we'll see cosine squared of theta minus sine squared of theta plus I times 2 sine theta cosine of theta. The real parts have to equal each other, and we get our formula. I really enjoyed learning about this derivation because it showed me theories which are a little bit more involved can very elegantly summarize complicated calculations. And it's a theme that I've seen over and over again in my mathematical path.